then another at n equal to half, n equal to 2, and then one at n equal to 3, namely 1/3, and so on, and there's an accumulation point of limit cycles here. They're all isolated, but they accumulate towards the origin.
Is X as a track?
Pardon me?
Is X as a track? I mean, when it goes to the one limit cycle, can it come out to the other?
Well, in such a system, if this is unstable, then everything will be thrown towards that or towards this. Everything to this side and this side. That's unstable. Then the next one will be an attractor. From both sides things will come in, etc. So the basins of attraction in this case are very easy to write down.
So question is very different. Is there any reason people find the limit cycles? I mean,
yeah, the whole point about dynamical systems is, what's the overall point here? The overall point is, independent of initial conditions, you want to find out what's long-term predictability. You always want to look at what's going to happen over long times. Short terms, you can integrate, you can solve numerically. Numerical solvability is not an issue. You want to know what's going to happen in the long run, always. Now, it turns out that in all these systems, where a phase space point ends up in the long run depends very sensitively on where it starts. That's what is meant by sensitive initial conditions. And we'd like to be able to identify all the regions of phase space which are attractors to which the system goes asymptotically and sits. Having done that, we would then like to find out with what frequency visits different parts of this attractor, so that I can replace time averages, which I may not be able to compute, by statistical averages over some prescribed probability distributions. That's the aim. That's the ultimate. In the absence of any information, you make a postulate. Like the gas in this room, for instance, has 23 particles or whatever. I know it's chaotic. Not only chaotic, but initial conditions, neighboring initial conditions diverge exponentially rapidly, with an exponent which is itself proportional to the number of degrees of freedom. So this Lyapunov exponent itself is of order Avogadro's number or something like that. So it's completely chaotic. In such a situation, I cannot do anything about time averages at all. All I can do is to look at invariant distributions. And I make additional postulates. I start by saying that in an isolated system in thermal equilibrium, on the energy surface, all microstates are equally accessible. Every region, every little cell in this energy shell is equally accessible. That's a postulate. I don't know how to derive it from mechanics, but it seems reasonable in the absence of information. And then you get the microcanonical ensemble, and then you say the density on this is just a delta function at h minus equal to e, and you proceed. So in the case of finite dimensional, or in the case of most dynamical systems, when I'm given the rule, I would like to find this invariant distribution from these rules alone. I can't put in an extra postulate like the fundamental postulate of statistical equilibrium, statistical mechanics. So that's my target. And for that purpose, I need to know which regions of phase space are stable, which regions are unstable, which are the attractors of this region, which are the repelling regions, what's the basin of attraction, which initial conditions go where, etc. That's generally what one is aiming for. And on the way, you'd like to identify limit cycles as well as critical points, as well as higher order attractors. Yeah.
So, is Mendelssohn criteria valid in higher dimensional?
Yeah, absolutely. Yeah, the generalization of Stokes' theorem. But it's used in 2 dimensions. There's an analog of it, but it's obviously very useful in 2 dimensions. Flow in a plane. In a plane, all possible flows have been classified and say exactly what goes on, because this thing called chaos is not possible for autonomous systems.
The condition that has to is on a closed orbit constant is 0. So, what you said in the last lecture that system which is dissipating, but you can sort of over a cycle the divergence of f.
Yeah.
If it is 0.
Yeah.
That looks like gives you a limit cycle, right?
In the Lotka-Volterra problem, it's not a limit cycle, it's periodic motion, but arbitrarily close to each periodic orbit, there are other periodic orbits. So a limit cycle is an isolated periodic orbit. In other words, you can find a neighborhood of every point on it in which there is no other periodic orbit. That's not true in the case of the Lotka-Volterra or the harmonic oscillator.
So So in this case, should we use the terminology asymptotically stable limits for these
Yeah,
dimensions?
yeah, one should say asymptotically stable.
Those are like stable limits, I guess. You have in the Hamiltonian.
Yeah, it's technically it should be asymptotically stable. That's really what we mean. Sure. Okay. You see, this program of identifying attractors, first fixed points or critical points, and then one-dimensional objects called limit cycles, and then two-dimensional objects called toral attractors, and then higher order tori, etc. This was imagined to be the scenario by which more and more complexity arises in dynamics. And in fact, Landau's original theory of turbulence said precisely this, that the system goes first into critical points, then it goes into a limit cycle, then it goes into a two-dimensional torus attractor, then an n torus, and then n keeps increasing, and finally you have chaos. Very irregular or turbulent behavior. But with the advent of chaos and the discovery that even at the level of n equal to 3 in phase space, you have strange attractors, you got other scenarios. And it's no longer believed that turbulence always occurs by the Landau route, but it takes place by this other Ruel-Tarkans-Neuhaus route, where there's a strange attractor. After the limit cycle, the next step is a strange attractor. So that sort of kills this very systematic picture one has that gradually the only mechanism for dynamical complexity is through higher and higher order attractors. That's not necessarily true. So in a sense, unknown has classified all possible strange attractors because they have really weird properties, as we'll see. All right, now I want to switch horses and go to Hamiltonian dynamics. I'm going to quickly go over the initial parts of Hamiltonian dynamics, which I assume are familiar to everybody. So this portion is just revision of standard material, but let me do this so that you have some completeness. Now, what is it that you're given in Hamiltonian mechanics? It has a very specific mathematical structure called symplectic geometry. And I should start by saying that that's the natural language to look at the Hamiltonian mechanics. In fact, I'd go so far as to say, one of the country's leading experts is here, Sam, that differential geometry and calculus on manifolds, I think we agree, should become part of the curriculum at a very early stage, at least in its elementary form. Because that's the natural language. And when you study calculus in that language, you realize that's the natural language in which a large number of these things are to be expressed. But since that's not true in general, I won't go into differential geometry at all. In any case, I'm not the expert on it. But I'll try to motivate where these structures come from, where the symplectic structure comes from, because it's important to understand that when you want to understand dynamical symmetry. So let's start with what a Hamiltonian system is. You're given a configuration space. Occasionally I use a little bit of jargon, just to tell you this jargon exists. You're given a configuration space, so let's look at systems with a finite number of degrees of freedom, specified by a set of generalized coordinates, up to Qn. And these fellows are elements of some space called some manifold, some nice manifold, called the configuration space. Some Q. I shouldn't use this Q. I'll use it for a canonical transformed variable. This is configuration space. Q for a minute. I don't know what to do. Now, this space could be curved. I mean, these could be angular variables, for example. So, suppose you have a particle moving on the surface of a sphere or something like that. Then this configuration space is two-dimensional, but it's not Euclidean. It's specified by a latitude and a longitude. But what we do know is that at every point on this space, there's a tangent plane. At each point, there's a tangent plane, and that's a Euclidean space with the same dimensionality as this Q. Okay. And that tangent plane, a collection of these tangent planes, is called the tangent bundle. The velocities live on the generalized velocities, the Q dots, live on this plane. In very crude language, with which one would try to explain this idea to a high school student, these vectors cannot be curved lines, right? So they can't live on the curved space, they have to be on Euclidean space, they have to be straight. Now you would call them contravariant vectors on this tangent bundle. but I'm not going to distinguish between contravariant, covariant, etc. This tangent space is a vector space, a linear vector space, and it's got a natural dual. This dual is called the cotangent space, and the collection of these cotangent spaces is called the cotangent bundle. So dynamics really happens on the cotangent bundle, which I'm not going to get into that language. But just for reference, what you call in tensor calculus vectors are really upstairs index objects, contravariant vectors in the old language. And what you call covariant vectors, namely the downstairs guys, they live in the dual vector space. And in the language of differential geometry, you have vectors and one forms. They're slightly different, but in Euclidean spaces which are self-dual, this distinction disappears, and therefore we kind of mix up everything, but technically one shouldn't do that. So just the rule of thumb to remember is the q dots are vectors, and the p dots are contravariant vectors, upstairs index, and the p's are lower index, downstairs index, or one forms. But I'm not going to distinguish between one forms and vectors in this case. So dynamics really happens, phase space is complicated. Mind you, I have not assumed the existence of a Hamiltonian or Lagrangian or anything. The moment you have a configuration space, there's a tangent manifold, there's a tangent space, tangent bundle, there's a cotangent. That's all that you need actually. But to make things concrete, you need to specify something more for a specific system, such as a Hamiltonian.
And the tangent space has the same dimension as the...
Yeah, it has exactly the same dimension. But it's Euclidean. And it's a linear vector space therefore.
In this case, what is the cotangent?
It's the dual. Now for a Euclidean space, it's self-dual. Yeah. But think of it as column vectors and row vectors if you like. Or as contravariant vectors and covariant vectors.
Sir, how is the manifold defined over here? We need the...
My definition of manifold is a very naive one. It's just the generalization of the idea of a smooth curve.
Over here in terms, explicitly in terms of QIs,
Yeah.
we require a definition over here.
Yeah, smooth is differentiable. I'm going to assume it's differentiable everywhere. So smooth surface, generalization of a smooth surface.
No, I'm saying explicit definition of the manifold in terms of QIs. Do we require something like that?
I'm not going to give it. I'm not going to do it. Yeah, because you can give such an explicit definition. When you start with calculus on manifolds, you do give such a definition. But I don't want to do that. I just want to use this intuitive idea that everywhere there is a tangent space. That's the only thing I need. Okay, yeah.
But the dimension of that plane is less than what is done.
No. This surface is two-dimensional. It's a surface. This is S2. Surface, not the interior. It's not a ball. It's a surface. Mathematicians call the ball the solid object, if you like, and the surface is the corresponding sphere. S1 is just the circle. S2 is the surface of a sphere which you happen to visualize by embedding it in 3 Euclidean dimensions.
Okay.
Pardon me?
So the entire configuration space is on S2.
The configuration space is on the surface. Like we move on the surface of the Earth.
So this particular example has 2 dimensions. So it's always necessary that the tangent space also be in the 2 dimensions. I mean, the same
The tangent space to a manifold at every point has the same dimensionality as the manifold itself. I can't draw a picture for what a 3-dimensional tangent space looks like. But it has exactly the same dimensionality.
How is this duality defined? How do you go from tangent to
How do you go in a linear vector space from ket vectors to bra vectors? You start by defining something called an inner product, which gives you a linear functional. Having chosen one particular ket vector, you create a bilinear combination which maps the vectors onto a set of complex scalars. That itself forms a linear vector space. And then the next stage you say this linear vector space for each of the chosen vectors is isomorphic, so you may just call it one linear vector space. And then say that the bra vectors themselves represent the quote-unquote elements of the dual space. This is what you normally do. But in Euclidean space, since it's self-dual, you don't make this distinction at all. You simply ket and bra vectors are mixed up, which is why you write A dot B is B dot A. But really speaking, that's not true. Really speaking, you know that phi psi equal to psi phi star. So when you include complex numbers, etc., you don't have this symmetry of this inner product. So it's in the same sense that I'm talking about. But a cheap way of understanding this is to simply think of it, the ket vectors as column vectors and the bra vectors as the row vectors.
Sir, I'm confused about one thing. The tangential space or the configuration space, it should be, is it unique or it can have any number?
Good point. Does the tangent space, is it unique here? If it's so, throughout the space, this means you can take a tennis ball and you comb it down everywhere without a cowlick. S2 has no unique tangent map everywhere, which is globally defined without a singularity, which is why you have a cowlick. Those of you who have hair know that there's one spot which cannot be combed. For people like me, the singular spot is expanded to fill the rest of the space. But S1 has a unique tangent map. You can go all the way around to come back to the same tangent space, and the way to say it is to say that S1 is developable or parallelizable. S1 is parallelizable, that means but on a sphere you can't do that. You try to roll it out into a plane, somewhere you've got to make cuts, which is why in this Mercator projection on maps you see this orange peel kind of shape with holes in it and so on. It's necessary to make a global map to do that. But locally you can always develop it into a plane, but not global. The torus is developable. The only SNs that are developable, and I'll stand corrected if I make a mistake here, Sam will correct me, S1, S3 and maybe S7. These are the only developable spheres. Okay. I want it to be parallelizable. Then I think this statement is correct. A single map, a single global atlas or a chart will do the work. Right? And that's because S1 is a Lie group. It's just SO2, a parameter space for SO2, and S3 is a Lie group. It's a parameter space of SO2 and so on. Okay. So now, given this, you also have the P-mods. Yeah.
When S2, the tangential space is not as the tangential space is not unit category. So what can be the number of the tangential spaces? How many tangential spaces can be there for, say, for example, S2? Is it specific or can be any?
Is it a unique? I think it's a unique tangent space, right? At every point, you need that. Yeah, you need the uniqueness of the tangent space. And for differentiable manifolds, I think that's always true. Yeah, tangent space is unique. The question is whether you take this tangent space, you make smooth changes to go to other tangent spaces, and you come back, will you come back to the same one or you come back to something else? Will you hit a singularity or not? And that's what is this famous statement that you can't comb a tennis ball. That S2 does not have a unique tangent map everywhere, which is, you need at least two. Yeah. The vector fields lie on, all vector fields lie on that tangent space. The q dots live on that tangent space. So you take a q here and a q here on the sphere, neighboring infinitesimal thing, then q minus q prime lives on that tangent space. So the vector lives there.
What's the problem? What's the problem that you can't comb the competence to that sphere?
Yeah.
So what's the problem? Where are we encountering the problem with this?
I can't find a single smooth tangent map by changing a parameter. I can cover all points of the space without a singularity. So that's the problem with S2. But it's not a serious problem. It's still a differentiable manifold. You can do all kinds of things. I'll use different charts. That's not a real issue. It doesn't have kinks and things. You see, that's the point. At every point, there's a unique tangent plane. That's all that I need. So we specified a set of Q's and P's, 2n of them. So right away you see immediately that the Hamiltonian dynamics n is 2. Now there's a huge difference, I said, between even dimensional spaces and odd dimensional spaces, and this is going to play a big role. Now immediately I should also add that Hamiltonian structures, and more generally things called Poisson structures, are known on odd dimensional spaces as well. But this is something I'm not going to get into at all. Purely mathematical thing. All our Hamiltonian space dynamics will be for finite number of degrees of freedom, even dimensional phase space. Now on this,
So
yeah,
what do you need even dimensional phase space?
pardon?
Even dimension because there are equal number of
Yeah, equal number, one for each. So what you're given in a Hamiltonian system is a set of 2n variables, and you're given a function h, which is a function of all the q's. I collectively call it q and p, possibly time as well, entirely possible, but a single scalar function called the Hamiltonian, such that the equations of motion q dot is delta h over delta p, and p dot is minus delta h over delta p. You're given this. Okay. And now this is a very special kind of vector field on the right hand side, because it involves just a single scalar function.
So one more
Yeah.
question. So we can go from a Lagrangian to a Hamiltonian
Yeah,
by a Legendre transform.
yeah,
But Lagrangian is a function of the tangent vector space,
yeah,
and this is a function of the cotangent space.
yeah, yeah.
So is the Legendre transform?
It's like going from one vector space to a dual. I mean, it's exactly
So
like that.
is the Legendre transform a dual operation?
Is it not? After all, what's the idea of a Legendre transform? If you want to specify, the crudest way of understanding Legendre transforms, like changing toothpaste. I have a function f of x. I can specify this function in two different ways. One of them is by telling you the value at each value of x, I tell you the value of the function. The other way is to say, no, I'm not going to do that. I'm just going to specify for you the slope of the function at each point. And I join them all together, and I get the function up to an additive constant. So if you tell me the value of this function at some reference point, then this curve is uniquely fixed. But that's the basic idea in a Legendre transform. Exchanging x for delta f over delta x, f of x for delta f over delta x. And you can generalize it to higher dimensions. And all of you are familiar that depending on what the external conditions are, you go from one brand of toothpaste to another. In thermodynamics, for example, if you use the energy representation, the microcanonical ensemble, then your independent variables for standard single component fluid objects are S, V, and N. And I make a Legendre transform. I don't like this. I go to TV and N, a function of TV and N. This, of course, is called the internal energy, and this guy is called the Helmholtz field. And I don't like this, so I can go to the enthalpy, which is S, V, and N, and so on, and so on. I can make several kinds of changes. I can change instead of V here, I can make it P, and then I go to the Gibbs field, P, P, and they're all Legendre transforms, based on taking first derivatives of some potentials with respect to other variables, thermodynamic variables, defining a new thermodynamic variable. So these are the most common, guys, but clearly there are other possibilities as well. There's the grand potential and so on. Can I, by the way, if I don't like this, I can go to a potential, phi, which is a function of S, P, and mu. Can I make a, just as a question, one of these interview questions, can I make a canonic Legendre transform to go to some, not phi, but some psi of T, P, and mu? Can I do this? Can I do that? I mean, I have three variables for single component fluid. Three thermodynamic variables are needed. And each of them can be chosen in two ways. So I have 8 possibilities. But normally you restrict yourself to 4. And then maybe you add a couple more. But can I do this? Can I start with the internal energy, make Legendre transforms? After all, this says dT equal to PdS minus PdV plus mu dN. So to this I subtract ds, I add PV and subtract mu n. And then I go to a function of Tp and mu. I can do that? Yeah, you get 0. So what's going on? What's happened? You lose all information about the size of the system. Because all these three guys are intensive variables. At least one of them must be an extensive variable to tell you how big this system is. It's gone, so you can't do that. You just get 0 as a thing. You get G minus mu n, but G equal to mu n, and you get 0. So even that mathematical thing, one has to be a little careful. But our immediate concern is not this, something else. Alright, so I'm given this, and notice that this is a very peculiar kind of equation of motion. Suppose I had x dot equal to the gradient of some scalar function of x. There too I have a vector field which is specified entirely by a single scalar function. So all the f1, f2, fn are all just components of this gradient here. But I don't have that structure here. In particular, this is called a gradient system for obvious reasons. In particular, you can see that the phase space velocity at each point is normal to the level surfaces of this function f. Whereas here, the phase space velocity will be on the level surface h, because h is a constant of the motion for autonomous systems. So it's very radically different. Although this vector field is still specified by a single function. And this minus sign will play a crucial role, as we'll see in a minute. Now, you're given this, and then you're given these so-called canonical Poisson bracket relations, which is simply a statement that these P's and Q's are independent of each other, such that the Poisson bracket, first I define the Poisson bracket of two functions of the Q's and P's. All of you are familiar with the fact that this is delta A over delta Q, delta P over delta Q, minus delta Q. Where there's a summation over the index I, which labels the degrees of freedom. I haven't put that here. You've got to put an I everywhere and sum over it. That's the Poisson. Now you might wonder why I'm defining a weird object like this, a weird thing like a Poisson bracket, because I take two functions of the phase space variables at a time and make them into a combination which gives me another phase space function, which is this right here. But some properties of this so-called Poisson bracket become immediately obvious. In particular, you can see that Qi, Qj equal to 0 equal to Pi, Pj, and Qi, Pj is delta. I'll call these the canonical Poisson bracket relations, and any pair Q and P which satisfies this equation, I'll call a conjugate pair. Now this Poisson bracket has some interesting properties immediately. The first thing you see is that A comma B is minus B. It's antisymmetric. You see another property, which is that A with some constant times B is just constant AB. And then if I have B plus C here, it just adds up. The Poisson brackets add up. I'm not writing them down. But more interestingly, the formula for derivation, the Leibniz formula, this chain rule works. So A with BC is A with C. I'll be disciplined and write this B here. Although it doesn't matter here. A with B. C. Why am I writing this B here? Pardon me? Yeah, when I go to quantum mechanics, I have to be careful with commutators. So this thing here, this derivation rule, this chain rule or whatever it is, there's one more property, which is the Jacobi identity, which is A with the Poisson bracket of B with C. That too is some phase space function plus cyclic permutations equal to C. So given this, we can write down, the Poisson bracket is extremely useful. We'll see its geometrical meaning. But it's very useful because it immediately tells you that if you give me any function of phase space, I can decide whether it's a constant of the motion or not, because its equation of motion for any QP becomes equal to A with H plus delta. That's easy to prove using the Hamiltonian equations of motion. Then it follows that this is a constant of the motion, this quantity, is a constant of motion if and only if this object vanishes identically. In particular, if A has explicit time dependence, then the Poisson bracket of A with H cannot be 0, it must be minus this. And we saw a simple example. So it's useful in writing